Welcome to the control systems playlist. In today's class we are going to discuss about one small topic, that is type number of control system, and after that we will see about a steady state error. Okay. So here already I have written this given loop. The given is loop transfer function, that is g of s into h of s is called as loop transfer function, which is equal to k into s plus z1 into s plus z2 and so on, divided by s to the power of n into s plus p1 into s plus p2 and so on. Here k is a constant and z1 z2 and so on z3 represents the zeros of the transfer function, and s to the power of n, the capital N here represents number of poles at origin. How it is, that is, for example, we have s to the power of 1. S to the power of 1 means that can be taken as s equal to 0, and if you can see the s plane, this is s plane, this is s plane. So in this s plane, if we consider s equal to 0, it is, here we take on the x axis sigma and the y axis we take imaginary, that is j omega, right. S equal to 0 represents a pole at origin. This is the pole at origin it represents. So the order of the polynomial here earlier you have studied, that is s square, s cube, like that, highest order. Here in this topic, type of the control system is decided based on s to the power of n, this capital N. If n is 1, one pole is present at origin, and if s n equal to 2, n equal to 2, two poles are present, two poles are present at origin. So this decide the type number of the control system. So one over other, if it is s square, we can say another pole on the same, we are going to have two poles, one blue color and red color, whatever is. So like that, s cube if you have, that is s cube if you have, that gives n equal to 3, that is 3 poles are present at origin. So that is type number of the control system is going to be 3. Like that you can have, if just n equal to 0, if n equal to 0, we have s to the power of 0, that is no poles are present at origin in the s plane, then we say that order of type, sorry, not order, type number of the control system is type 0. So we have this type 0, if this type 0, if n equal to 0, like that we can write type 1, type 2, type 3 if n equal to 1. Similarly type 2, like this we can write, okay, n equal to 2 and so on, we can have type of the system. So what it is finally deciding is, we have the denominator polynomial in the given loop transfer function, that is s to the power of n into s plus p1 plus s plus p2 and so on. So n, capital N, is present in the denominator polynomial of the loop transfer function. So that capital N value decides the type number of the control system, right. Now we will see steady state error, right. It is another topic in the control systems itself, very important. We have steady state error. So this where we get is, when we apply an input to a system, we are going to get some error at the output, that is exact. If you take some measurement system we have, instrument we have, we are given some 5 volts input. If it is voltmeter or ammeter or power meter, anything we are going to measure some value, some parameter we are going to measure, the value which is voltage, suppose we want to measure, actual value is 5 volts, but the measured value is 4.9, 4.8, 4.95, like this. So that means there is some error is there, that is when compared to the actual value. So that is error. Now at steady state error means at t equal to infinity ideally we say long time, after a long time we are going to decide this is the final value which is measured, and this is not exactly equal to what we have given at the input which we want to measure. So there will be some difference. So that difference is the error. At t equal to infinity, whatever the error we get, that is called as steady state error. So for that we consider a block diagram from which we take the error. So we know the closed loop system we have. Input we have RFS. This is a closed loop system. Closed loop system we are going to consider now. Closed loop system, and this we have the input RFS. Here we have plus, and this is G of S, the open loop transfer function G of S. Then we have the output. Now we are going to take the feedback from output towards input. In between you are going to have H of S. Okay, so this H of S along with C of S gives the feedback signal, and we are going to give here it as minus to the summing point. So here we have minus, which represents a negative feedback, and here we have H of S. Now at this point we are going to get C of S into H of S, which is called as the feedback signal. This is called as feedback signal. This is feedback signal. RFS is input signal. RFS is called as input signal, and here the difference between RFS and CFS and HFS, which is called as E of S at the output of the summing point, that is called as the error signal. Okay, and now CFS is nothing but our output signal or output response, we are going to say. Right, now we are going to take what is E of S equations. We are going to write E of S is the output of the summing point, which is nothing but R of S minus C of S into H of S we have. E of S is equal to, you can see here this which I am making with the black color, this is E of S, which is equal to, from the input we are getting R of S, and from the feedback we are getting, I am making the pink color, you can see C of S into H of S. R of S we have plus sign here, C of S into H of S we have minus. So E of S is the output of this summing point, which is nothing but R of S minus C of S into H of S, and we have the output C of S. Okay, this E of S is the error signal, and we know what is C of S. Here we can see, if you take this, I am making dark here, C of S is nothing but E of S into G of S. E of S is coming as the input to the G of S system. So C of S is the output signal, right? C of S is the output signal, which is equal to, C of S is equal to R of S into, sorry, it's not R of S, C of S is equal to E of S into G of S. This is C of S. Now we are going to substitute this. Suppose take this error signal equation as equation 1 and this C of S equation as equation number 2. Now we are going to substitute equation 2 in equation 1. We are going to substitute equation 2 in equation 1 we are going to do. So we write here E of S is equal to R of S minus, you can see equation 1 is C of S into H of S. So in the place of C of S we are going to substitute equation number 2, that is E of S into G of S into what we have is H of S, into H of S. Now this negative term on the right hand side we are going to bring on the left hand side. So we get E of S plus E of S into G of S into H of S, that is equal to R of S we get. Now you take out E of S common from here. So we get 1 plus G of S into H of S on the left hand side. So that is equal to R of S. So from this we take this 1 plus G of S H of S in the right hand side. So we get in the denominator of R of S. So we can write it as E of S is equal to R of S whole divided by 1 plus G of S into H of S. This is error signal E of s we got finally. Now this is in S domain, we want to get it in the time domain. So to get this in the time domain, we are going to apply inverse Laplace transform. We are going to apply inverse Laplace transform on this. So then we get the error signal in time domain. So E of s, L inverse of capital E of s is denoted by, here in time domain when we write, it is going to become as E of t. So E of t is the error signal in time domain. So we are going to apply the inverse Laplace to this also, that is R of s by 1 plus G of s into H of s also. So therefore E of t is equal to L inverse of R of s whole divided by 1 plus G of s into H of s. This is we get. This is L inverse. Now this E of t is an error, but we want to have steady state error. Steady state error, it is steady state error means at t equal to infinity, ideally it is after long time. Steady state error is denoted by ESS. SS represents steady state error. So which is defined as when t tends to infinity. Okay, the steady state error is defined as, ESS is defined as when limit t tends to infinity, that is at t equal to infinity, the E of t becomes as ESS, steady state error, it is at t equal to infinity, right. Now here we are going to use the final value theorem of the Laplace transform, so that this is simplified further. So the final value, I'll write the final value theorem of the Laplace transform because you have studied long back. I don't think you remember or not. So first I will write the final value theorem of Laplace transform. What it is, I think you remember it is okay. If f of s, some function we have which is in a frequency domain, which we obtained by applying Laplace transform of f of t. F of t is in time domain. If you apply Laplace transform on that, we get f of s. Then this is a theorem, limit t tends to infinity, f of t, that is what will be the f of t when t tends to infinity. By applying final value theorem, it becomes limit s tends to 0, s into f of s. So this is what the statement, general statement of final value theorem, which we are going to use in case of steady state error, so that we can easily obtain the frequency domain response. So if we apply this final value theorem with respect to steady state error, so now we are going to apply final value theorem. Final value theorem we are going to apply on steady state error. SS I will write, and then you can write steady state error. So what we get, ESS is equal to limit t tends to infinity. Here E of t is nothing but f of t, you can consider. Limit t tends to infinity, E of t is limit s tends to 0, s into E of s. So in place of E of s, earlier we had f of s. For general case, you can see here limit t tends to infinity, here we have limit t tends to infinity, f of t gives limit s tends to 0, we take s into f of s. So in place of f of t, we have taken E of t, and in place of f of s, we have taken E of s. That is what we have written here. So E of t is, again I am telling, f of t, and E of s is nothing but f of s. So this is from final value theorem. This statement we are going to use for deriving in static error constants, which we will see in the next class. Thank you very much. Please subscribe and